Alright guys, so this is part 2 of the lecture for 3/18, so March 18 for spring of 2020. So the first part is posted on Canvas. I suspect that this will be posted on YouTube because right now with all the videos that I posted there, I don't know how to make it like small enough such that I don't take up all the space on Canvas. So yeah, so this should be on YouTube. So last time on the first part, we went over, that's better over there. We went over the theory for compressors and pumps, and then for heat exchangers and mixers. So it was this, and this is posted, and then this one over here, which, they are not the clearest notes because they're meant to be for me. So they're not very elaborate with, a lot of definitions and so on because they're my notes. However, I told you guys a lot of information, and then I posted some recommended problems. And again, if you're looking at the folders, is the one that says online class, at least my part of the online class, and then it says recommended problems, and the solutions are posted either on that file or if it's old exams, on old exam files. Okay? Right, on the third part of this set of notes that I posted, there was a page that had, that was bad, that had examples, okay? So we're gonna go over those examples. All right, so Dr. Mikolaitis is the one who's going to substitute for me. He's supposed to take over the class and do his own thing, right? Like decide what to do with the 50%, decide what to do for exams and so on. Like I'm supposed to just be free to rest and recover. Well, he's been asking me all these questions, like can I make one of the exam problems for him for open systems? Not make it, like recommend. He might be watching this, so I should watch what I say. And he wants my input, like he's thinking of giving no homework again and doing like 2 more exams, 25% each, where, you guys already have 50% out of 50 on the one before, the first half. So I think it's going to work out. We really, like so far, we really get along. I was his TA a few years ago, and we really get along. All right, so I posted the solutions to the problems that I'm going to go over now. And I am hoping that I did this in order because I don't have them in order with me. So what I'm going to do now is check. So you're looking at me looking at the computer weird. It's because I should have done this before. I'm going to check that I posted these problems in order. If you look at the problems, it says online class, not recommended problems, instructor notes, and then 318 part 1, 318 part 2. On 318 part 1, the last part is the one that says examples. Then after that, part 2, just start with a compressor problem. Very good, compressor problem. And then after that, the same compressor problem solved with constant specific heat. So make sure that you have this, then the one with the pump, and then one with the heat exchanger. All right, so we're going to start with the compressor one. I've wasted enough time already. Don't touch your face like I'm doing. I just say, all right. Okay, so it says assume, reading this, okay? Assume steady state, one-dimensional flow, not flow. Simple compressible system for water, ideal gas behavior for air. This is quasi-equilibrium. We didn't talk about that. It means that the processes occur not at equilibrium, but if we take a process and separate it into a lot of smaller processes, we can say that each one of them occurs at equilibrium. And that's what we've been doing in the class. Something I should have mentioned. I was thinking of mentioning this later when we got to the second law. So Mikolaitis might bring it up. Since Mikolaitis is going to lecture using that online thing on Canvas, just stop him and say, she didn't really go over this, and he's gonna judge me. That doesn't matter. Then he can just go over it with you, what that means. Because in reality, processes do not occur at equilibrium. This is an assumption that we make to be able to use all of these equations that we're using. And then when we get to the second law, we realize that life isn't perfect, things are imperfect. We have been making all these assumptions like Q0 for a turbine, and we have to use this isentropic efficiency for it, and just we start making things more realistic, okay? So ask him about that if he brings it up, okay? All right, so 5 minutes and 45 seconds into the video, finally, we get into the example. Air flows through a compressor entering at 105 kilopascals, 1.05 bar, 300 Kelvin, and then a volumetric flow rate, AV, equal to 12 cubic meters per minute. And then it exits at a known pressure and temperature higher, right? And the compressor has heat losses. Oh, no good. Because then we can't use the equation from the handout. When I refer to a handout, it means for like the old files, right? When we look at the folder of handouts, I think, and there's one that's called supplemental or something like that for open systems, okay? And it tells you that the magnitude of the heat losses is equal to 2 kilowatts. You want to find the power required by the compressor using constant specific heats. All right. And then it says redo it using variable specific heat. So if you look at the notes that I posted, the very first one is solving it a variable specific heat. All right. So this is something that you should practice on your own. All right. We're going to do it solving it for, this is variable specific heat. So we're going to solve it using constant specific heat. So the procedure starts the same way. Okay. You can notice that I almost threw this away. An accident. Maybe not an accident. Okay, so the procedure starts the same way. It's just variable and constant specific heat. It means that we will solve H. We'll solve for H a different way. Okay. For delta H, instead of using H straight from the table, we'll use that delta H, Cp delta T. But the first part of the procedure for both of them is the same. Right, setting up the conservation of energy equation and simplifying it for the assumptions that we have here. So we start conservation of energy, and if we look at the handout that we have, the equation for power of the compressor is m dot h1 minus h2. However, now we have heat losses, which means that we need to start with the original equation. And I still tell you, you should, I don't think Nikolaitis is going to get all creative with his problems. He's actually pretty straightforward, and he's extremely smart. You'll see. He uses 10 times as many big words as I do. Maybe 100. Just many more. Anyway, so I don't think he's going to get really creative, like give you a system where he wants you to start with the original equation and figure out what's happening and a bunch of stuff. But you never know, and you should know this. We start with the EDT, like I've been saying in the last videos. And we have the EDT equal to Q dot minus W dot plus the summation minus the summation. And then we get that equation. Okay, this one over here, right? Because the EDT is 0. And I don't have any change in velocity or changing elevation. Now we have to take the signs into consideration for the direction of Q and W. So this is the top part for some students, right? We have that 0. We have for Q negative. For Q out, it's negative. And then we have the negative from the equation. And then work in is negative. Okay, we need to include those signs. We need to. Otherwise, the result for work will be wrong. Okay? And then we have plus m dot h1 minus h2. In minus out. Okay? And then we end up with the equation for power, which is Q dot plus whatever. Now, delta H, and this is old material that you might have on the ideal gas handout. Delta H is Cp delta T for an ideal gas, and it doesn't say find Cp at any given value, so we find Cp at T average if we have the two temperatures we do. And a T average is 350, so from table says A20, but it's from A17. Pretty sure it's A17. We can find CP the way we found it before. Yeah, and it's 1.008 kilojoules per kilogram Kelvin, okay? So now we have CP, we have T2 and T1, Q dot is given, we already incorporated the sign. So now the only thing that we are missing is M dot, all right? M dot for one-dimensional flow is AV times density, which is the same as AV divided by specific volume, which for an ideal gas is equal to PAV divided by RT, okay? Again, this is old material, but I understand all the situation is stressful for you, so if you don't remember, well, again, that's not new, okay? Now we have to be careful with the units because AV is given with minutes in the denominator, which can just mess it up for us. And then if we're careful with the units, we add M dot. Once we have M dot, we have everything that we need and we can find power, okay? If we had messed up the signs, no, I would have gotten 24.6 or just something that did not make sense. Now, what would happen if that Q dot is 0? What do you think? I don't have to give you time to think. You can pause. Well, if Q dot is 0, then all the power that is supplied to the compressor is used to increase the energy of the fluid, which means that we would not have to make up for those losses, so we would need less. 2 kilowatts less, exactly, okay? It will be 24.6 kilowatts. We would need less, just the amount required to increase the energy and nothing else required to make up for other losses or for losses, okay? Now again, this is constant specific heat, variable specific heat. Yeah, for variable specific heat, it's the same. It's just that I found H at the tables, all right? And here it says A22, but it will be A17. And this one actually, what it says A20 is A2, okay? And that's not meant to be confusing, okay? This, again, I was using in our textbook to solve these problems. So the tables that you remember that we need for ideal gases is A2B, all right, for constant specific heat, to find CV, CP, or to find K. K is CP over CV. Nikolaitis likes K. K is CP over CV. When you encounter things that are a little different, just ask him. Feel free to ask him or send me an email. Or send me ask me a question where other people can see, okay? And the other table that we have is A17. So if you see other numbers here, again, this is what I don't post my notes, but you guys know what the tables are, okay? Now the next example, I can only post 15 minutes at a time on YouTube, so I only have a minute and a half. So I'm just gonna read it. It says that we have water entering a pump and it's saturated liquid at 50 kilopascals. And the pressure is increasing through the pump and the density remains constant. And the final temperature, so it will be at the exit, is 85 degrees Celsius. We want to show this on a TV diagram and we want to find the specific work that the pump requires, okay? So this problem is with water, so it's different. Now we have a pump, we have the inlet and the exit, and to find the work required by the pump in those units, all right? Kilojoules per kilogram. We need to modify a little bit the equation that we have on the handout. Now we can see from the problem statement that there are no heat losses, no change in velocity or elevation. So we can use the equation that we have on the handout. Power of the pump M dot H2 minus H1. So that power of the pump from the handout, come on, I have very little time. This one over here, this, all right, this one. From the notes, just power is kilowatts. That's kilojoules per second. And M dot is kilograms per second. So if I divide kilojoules per second by kilograms per second, I get kilojoules per kilogram, which is specific energy, all right? Or specific energy transfer in this case. So that's how I'm going to start that problem. To be continued very soon. Okay. Thank you.